Okay, so in this video we're going to talk a little bit about convex lenses. These are also called converging lenses for reasons that we're going to see in a moment. So the first thing we can do is just note that I've already drawn out a convex lens, and I've drawn out a couple of axes as well. So we've got an axis going straight through the middle of the lens, kind of in the X direction, and then lengthways along the Y direction of the lens. And the first thing we're going to look at is this idea of what its properties are and how we define how strong its interaction is with beams of light. And of course we're going to assume that this material of the lens is going to be usually acrylic or sometimes glass. In either case, we're going to have a material that has some index of refraction that's going to bend, it's going to refract light. So the first thing we're going to do is have a series of parallel rays of light coming in to this lens. We have a source of light on the left hand side, and that source of light is going to have parallel rays. I'm going to try to draw this reasonably symmetric. Okay, I'll draw one over the axis, but it'll be hard to see. And just to be kind of clear about what I've drawn, I'm going to have little arrows here just to denote that we've got rays of light there in blue. Okay, so we've basically got some flashlight or some source of light here. It's going to come and impact the lens, and what's going to happen is at this interface it's going to refract, and then as it exits the lens it's going to refract as well. But we're going to do something because it's going to be this thin lens approximation. I'm going to treat it as if all the bending of the light rays occurs right in the middle of the lens, and that helps us simplify these ray optics diagrams. We call this ray tracing, where we can have some continuous beam of light, but we're just going to have some examples representing the path of that light. So what happens when it enters, when light enters this convex lens, is that we get this bending towards a central point. So it's going to converge on a point, and we're going to think about the fact that this beam here is going to intersect that surface, that curved surface, but at that exact point in the middle. And we're going to assume this is nicely symmetric. I did the best I can. And we're going to assume that right here, this is actually going to be essentially flat, so that it's going to, the incident angle here is going to be 90 degrees, so there's not going to be any refraction. And then as you move farther and farther away from that center point, we're going to have more and more curvature, so we're going to have more and more refraction because that angle of incidence is growing. Okay, so if we look at where the rays are going to end up with, they're going to bend towards the axis. Like this. So we'll have one ray bend, so it'll be coming in like this, and we're going to have all the other rays as well. Draw little arrows to make sure it's clear what we're actually doing. Just drawing these rays of light. Okay, so this is the behavior of light as it enters this convex lens. And we see that it's all converging. All these rays are converging at a very particular point. And this is the focal point. And we can do this experimentally and then measure, well, what's the focal point of the lens. And in this case, it's basically 3 centimeters. And I actually noted this here at the top. And oftentimes you're told, because this is giving you a sense of how strong that lens is. If we were to use a denser material, something that does more refraction, we could, or we could change the curvature here, and we could change just how much refraction we get and where the convergent point is. So a weaker lens, we would get kind of a convergence farther away. A very stronger lens, we get convergence very close to it. So this is 3 centimeters focal length out to this point. So we can kind of label this if we want out to here. This is our focal length, and in this case it's 3 centimeters. Now, this is a symmetric lens, and so there's also going to be a focal point on the other side at exactly the same distance. So I'll just label this as F, and we're going to have that up here. So this is also going to be a focal point if we were to direct light in the opposite direction. All of this would be reversed. It would be a mirror image, and it would converge at that focal point. This is going to be significant for some images when we look at, well, how do we actually create an image out of these types of lenses? And that's what's coming up next.